AC to DC converter. So today we are going to discuss about the AC to theory which lag So here is all about the AC to DC converter. So first of all, we need to understand, so why is an AC to DC converter is required? So all of you know why it is needed, AC to DC converter? Anyone is having any idea about that?
Ma'am, mobile phone cannot charge directly to AC.
So anyone is having any idea?
Yeah, plant runs on DC power. That is why we need AC to DC converters.
First of all, am I audible, everyone? I don't think it is audible because no one is responding. That's why I'm asking.
Yes, ma'am, you are audible.
Lag, ma'am, I think there is a delay between I am saying and you are listening. Big delay.
You are responding, I think it is not audible. Okay, just wait. Because I am not able to listen. Yes, I am not. Voice is not reaching you. Yes, just wait. I think there is some issue. So now it is audible.
Yes, ma'am, are we audible?
Now it's audible. Okay. Yes, now you all of you are audible. I think there is some issue. Okay. So we can continue. So here is the second model is all about the AC to DC converter. So anyone is having idea? So where we are going to choose the AC to DC converter?
Ma'am, every appliance runs on DC. That is why we need AC to DC converters.
Ma'am,
So where it is
appliance.
Any applications you know?
Ma'am,
every appliance except fan and I think every appliance except fans and some kind of specialized appliance for AC power, except all of that, every appliance runs on DC power.
Okay. So
ma'am,
just simply I'm
appliance.
just going.
Ma'am, I think appliance which need a constant power means throughout their working period, they need DC. The rest will work in AC.
No
Okay.
appliance
So
runs on AC, ma'am, except fans and some appliance.
We can talk about the industries. That is very useful for that. I think those who have know about the RSPs, we can say some industries. So where it is typically used the AC. Okay. So let me just give you some few examples. Suppose. So here is my connections. Suppose.
We are not able to see, ma'am. You're sharing something else.
Not able to see?
We just
is it visible?
Authentication keep alive of the Wi-Fi. We are seeing the authentication keep alive of the browser.
Okay, wait. सेटा बंद कर दिया है ना So this is visible for today we will discuss the AC to DC converter. So now it is visible to everyone?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Okay. So question arises, why is an AC to DC converter is required? So let me explain you. So you can see here is our plug point and which is we are going to give the AC supply. So you can say the 100 volt. And what is the AC to DC converter? Is a switching regulator. Switching regulator, which is going to switch from the AC to DC. So with the help of, because we are going to give the AC voltage, so AC supply we are giving, that's the 100 volt, but through this regulator we are going to transform the AC to DC, then we can say we are having the DC voltage, so we can say that 12 volt. So now after giving the 12 volt, that's the excited DC voltage, we are going to give, it is a 12 volt to 24 volt. So as per our requirement, so we are going to use over there. So now this all three are, we can say the DC to DC converter, and these all three are known as the linear regulator switching, and which is nothing but the DC to DC converter. Suppose we are going to go for, so here is suppose give you the 3.3 volt, it is used for the microcontroller. Suppose I am giving the 5 volt and that is used for the LED. To glow the LED, so we need the 5 volt DC supply. And for to turn on the motor, we are going to give that 12 volt. This is for the motor. And for the first one, 3.3 volt is for the microcontroller. So that's why what is needed, because we can say our electricity supplied to homes is typically the 100 volt or the 200 volt. Okay, so here we can go for the 100 volt or the 200 volt is the supply. But for most of the electronics operate at the 3.3 volt or the 5 volt. Like we have discussed 3.3 volt for the microcontroller and we decided the 5 volt for the LED. And the 12 volt just to turn on the motor. So now, but it is constantly, because we need the constantly conversions from the AC to DC, so we need some motors or the lamps. So motor is just to help with the start of the system so that it can gives you the output in a positive way. Suppose if you are done in a lab, the DS labs, so all of you know for the light glow, we are going to give the 5 volt of the LED. Suppose it doesn't glow, that means we are going to give the 0 volt. That means there's a no supply is there. So that's why at least our rated voltage to turn on the LED is a 5 volt and to turn on the motor or to start any kind of electrical circuit, so we go for the 12 volt the DC. So we can go for the motor which includes the control circuits. That means for the 3.3 volt the microcontroller, we are going to decide or we have give you the this much of the 3.3 volt. If it exceeds the 3.3 volt or exceeds the 12 volt, that means it's going to burn out the microcontroller. So that's why we just give the 3.2, 3.3, 3.5. This is okay. So now for the LED, we are going to go for the 5 volt. Suppose lamp. Why the lamp is required? So lamp which can be switched to energy saving. So LEDs are just we can remember that just to turn on and the turn off very quickly. So that's why we're choosing the LEDs instead of the lamps or the normal bulb. So that's why to convert from the lamp which may be switched to energy savings, because initially traditional way we are using the bulb, that must be converted to energy saving LEDs. So that's why we are going to choose the AC to DC converters. So here is why the AC converter is required. Now we go for why we need the AC voltage. So why we need or why we send the AC voltage? Now question is why send AC voltage? So what are the product we got like the microcontroller, LEDs, and the last one is the motor. We give the 5 volt. There is the 12 to 15 volt. For the microcontroller, 3.1 to 3.5 volt. So these are the some electronic products. So we can say so the device are the DC parts. All are the DC. So the electricity is generated at a power plant. So suppose let me tell you. So here is a power plant. So here is the power plant, and we are having going to give the supply. In the output side, we need the load for the basic any kind of the circuit. So we can generate the electricity. This kind of the power plants like the hydro power plants. We can go for the thermal power plant. This is a few plant. So all the plants having the common things. What is the supply? What is going to give you the supply for the suppose here our HPC converter. We are going to give the AC supply so that we can get the DC output over here. So we can say that all the hydropower plants or the thermal power plants or the nuclear power plants all are placed or located at the means we can say the coastal areas. So what is the making of it? So it can be the more advanced to send the AC voltage to an urban areas because it's not useful for the our we can say the metropolitan cities. So that means the transmission of the high voltage. It means this industry, all the industries, the nuclear power plant, so all need the grid concept. The grid concept is required as to transmitting. So grid is required to transmit the AC voltage, but at the low current. Transmitting the AC voltage at the low current. We need the low current just to pass the high AC voltage, which can minimize the transmission loss. So that's why the grid concept is going to added. So that the grid concept is there. Suppose here is my grid. It is placed. Suppose here is my grid. So these are basically going to help you to transmit the high AC voltage, but with a low current. That means if you give the low current, that means minimize. What is that minimize? Minimize the loss. So what kind of loss? The transmission loss going to be minimized while giving the. These are all other grids. So that's why, because all our plants are present located in the urban area, that's why it is very advanced, or we can say it's the advantages for us to send the AC voltage to that area. So since the transmission of the AC voltage, because we are going to give the high AC voltage, that means we cannot be used in the home because it's only for the plant area, but we cannot give the high AC voltage to be the home. It is transfer. That means we are going to step down. Step down. And another one is the step up. Step up, that means we are going to increase the output voltage and will give the input voltage at the minimum. But for the step down, we are going to give the input is the high. It means our work for the because we are not going to use the AC at the home, so we need to step down. Okay, that means the output voltage is less over here. So the several substations we can say, we can grade, we can also say the substations before reaching the 100 volt and the 200 volt at the outlet. And this type of the transformations voltage also sent via the AC, since the AC is the easier to transmit. That means we need to step down our voltage. It's all about the AC signals. So now AC to DC converter, and which is nothing but the uncontrolled rectifier. We are going to discuss about the uncontrolled rectifier, and one is the controlled rectifier. Here is the controlled rectifier. So in the controlled rectifier, we are going to use the thyristors. Different thyristors we are going to implement. And for the uncontrolled rectifier, which are based on the diodes. And here is the rectifier which is going to convert the AC power to DC power. And here is the rectifier divided. Here is the uncontrolled rectifier and is the controlled rectifier. So we need to understand why it is the uncontrolled rectifier. So we'll discuss the one by one. So first one is the uncontrolled rectifier. So first one is the uncontrolled rectifier. That means the uncontrolled rectifier which can use the uncontrolled power electronic device. That means we need the rectifier which needs the uncontrolled power devices. These are known as the uncontrolled rectifier. That means the uncontrolled power devices means diode. So here is the diode, here is our anode, and here is the cathode. And here is how the current directions is the IA. There's nothing but the anode current. So the diode is one of the uncontrolled power electronic device, and which can be conducted based on the voltage at the terminal. That means we need to make VA must be greater than the VC. That means the anode voltage must be greater than the VC. That means we're going to go for the forward bias conditions. But when the opposite came, the VC is greater than the VA, it becomes the reverse biased. The current becomes also reverse biased. So here is the conduct based on the voltage from the one terminal to another terminal. And you can see here are the two terminals are there, the anode terminal and the cathode terminal. But it cannot be controlled by the control signal. Why it is not controlled by the control signal? Because here only we are having the two states. It means we are having one is the on state, another one is the off state is there. So determined by the power circuit. For here that is it is required. It means it doesn't need any kind of the control signal just to turn on and turn off, because there is a one way is there just to turn on. That means the directions must be the unidirectional current that is the VA must be greater than the VC. So we can consider that is the on state, or we can say the forward bias conditions. When this reverse came, so it became the reverse bias, and the current direction is also going to be the negative. We can say the minus A. We can say so. That is the no control signal is required. But for the control rectifier, we just need the thyristors. So control rectifier, we need the anode, we are having the cathode, and we are having the gate pulse is there. But here we need the control signal just to turn on and the turn off the thyristors. But here doesn't need the control signal just to make straight turn on and the turn off our diode. So here is all about the uncontrolled power devices. So up to this much, everyone is clear? Is it clear to everyone?
Yes, ma'am.
Okay. And for the control rectifier, so we need the power control devices like the SCR. For the control rectifier, so we need an SCR. For the thyristor, and that thyristor family is a triad, IGBTs, SIPs, so etc. We can choose any one. So it it can be converters. We can go for any kind of the converters, step up and step down converters. We need motors, okay, and inverters or the DC drive. So the come under the control rectifier or within the thyristor family. So, and it can be also by using the SCR, because here we are giving the control signal. Here with the control pulse we are going to give due to the gate is required. Gate pulse is here. So, what is going to happen if we give the gate pulse? So, we just need to measure the firing angle. We need the firing angle alpha, and need to measure the pulse with modulations is going to be observed, get to be controlled. Power and modulation going to be controlled. These are depending upon the which thyristors we are going to use for the SCS, RIAC, IGBTs, SITs, etc. Whatever you are going to use, or any kind of the converter, just to make sure that we need to control the pulse by using the gate pulse is there. So we need to measure the firing angle. That means each interval, the complete cycle. So here is my complete cycle is there. So 0, here is my pi, and here is the 2 pi. So here is the positive half cycle and here is the negative half cycle. So depending upon the positive negative half cycle, so we are going to check whether the whole the rectifier system, the converters is going to be correctly or the not. And we need to check at each firing angle. That means suppose I am going to consider what kind of a circuit I am going to use, because for the control rectifier ACR is going to use. It means we need to check each to turn on the system. We need the gate pulse is required to get the output. So here is the output and here is the input. It's a DS. It's a sinusoidal signal. So let me go for the each half cycle. I am going to check the what must be the output. The positive half cycle is depending only the diode is there. Maybe it's going to the similar with the input. The VS voltage. Here's the VS and here is having the minus of the VS. So what is the firing angle over here? That means we are going to check for each and every interval of the time. So let me check you. Here is the pi point pi by 2 and here is the minus pi. We can consider this the minus pi by 2. Suppose this is the positive half cycle, negative half cycle. For here we need to check for this, because this is the maximum point. This is the where see the maximum or the peak point over here. Here is the peak point. So from 0 to this peak point, what will be the conversions, what will be the voltage, and what is the voltage value, and if there is any kind of the different components are there, suppose diode is there, that we are having only R value is there, or we are having the L and we are having the C is there. So depending upon this diode, resistor, capacitor, these are all the values we are going to check whether the output is going to be going increase linearly or is going to become downward. So we need to check for the each firing angle. That means we can going to obtain for the this interval of the temperature. So we can consider here is our firing angle is there. It means the conduction part we can consider for the to check the firing angle. So okay, so diodes based the uncontrolled rectifier and thyristors are come under the controlled rectifier. So again, rectifier is the divided into two parts. So rectifier is divided into two parts. One is the half wave, another one is the whole wave rectifier. In the half wave, here is the current in one direction. Current in any one direction, so one line, and it is connected to an AC source. It is connected to an AC source. Connected to an AC source, and that is the unidirectional. So here is the unidirectional, and for the full wave we are having the bidirectional. Bidirectional. That means for the half wave we are going to go for the only the positive half cycle, and for the it is the unidirectional and it is the bidirectionals which can connect it to an AC source. So any kind of a rectifier, it may be we can say the one pulse or two pulse or the n type of pulse is depending upon the pulse. Depending upon the pulse, because as you have remember, we are going to measure the pulse width of the modulations. This is going to be helpful. So how you are going to measure the pulse for any kind of the rectifier for the pulse, for the half wave type of the rectifier and for the full wave type of the rectifier. So depending upon the pulse, that means we are going to measure the pulse number. How we are going to find out? That means we are going to find out the number of the load current. That means our output current, the output current or the voltage, which is going to be measured during the one cycle, during the one complete cycle of the AC source voltage. So you are going to take the AC voltage, supply is there, and we are having the load is there, which must be our DC. So for each complete cycle, we are going to find out what is the number of the output current and what is the number of the voltage, and that defines as the number of the pulse. So we are going to discuss the single phase, the half wave rectifier. So here is our single phase half wave rectifier. So here is the single phase half wave rectifier. So here is a single phase half rectifier with the R load. What is the R load? This one is the R load. So at the output side we are having the load is in terms of the R. That is why it is known as the half wave rectifications with the R load. So while it is a single phase half wave rectifier, that means it is also the uncontrolled half wave rectifier. That's why we have chosen this as a diode. If we go for the single phase half wave rectifier for the controlled, instead of the diode, we are going to place the thyristor. So because the diode is very widely used rectification circuit, because only just to check to measure the small pulse, because due to this diode, we are going to measure the small power level. So here the output is heavily affected by the reactance to the connected to the load. Because reactance is all about the R, L, and C. Instead of the with the R, we can consider for the L and the C. That is going to be measured. But here only we are having the R is there. So that means what is the advantages while we using the R load? So R load using with the diode. That means what is our work? That means our rectification process, which is going to convert from the AC supply to a DC by using the diode. That means, as we know here, the half wave rectification, the current directions, the unidirectionals in build. That means to make the PN junctions, we can say. So for the PN junctions, convert is the bidirectionals, because if you remember, we are having the P and N junctions. Here is our P and N junction, and the middle one is our depletion region. Here is our the depletion region. Here the current directions is depending the unidirectionals. Here is our VA supply. Here is the VD is the triode voltage, and V0 is the output voltage. And depending upon this output voltage in the current, we are going to check the what is the number of the pulses we are going to use. So we can say here the circuit, or we can say it is a configuration. Here is the configuration is there. that means we are going to consider for the positive positive supply. So here is our supply. It is the positive, and here is the negative. So here is the input is we are going to give the positive and the negative supply, and where output is going to be, because we are going to consider the unidirectionals, that means we are going to go for only the positive cycle. It's the positive half cycle. For the positive, we are going to consider. That means rectify the output waveform. That means the no negative half cycle we are going to consider over here. So So for the single phase half rectifications, we are going to consider only the positive part because it is going to be the unidirectionals, and we are going to rectify the we can rectify the output voltage. That means instead of what in which directions diode we are going to use. So we may going to consider for the forward bias, we can consider for the positive half cycles. And if you are going to current direction, so the voltage direction is opposite of that. That means you are going to consider the negative half cycle for that. So now, initially you are going to start the positive half cycle of the AC supply waveform, and, we are going to eliminate the negative supply. So, this is for the current directions. Suppose my reversing the directions of the diode direction must be reversed. It means it is going to pass the negative voltage. The directions must be negative. So, we are going to design. It means when the diode reactions is the reversing, it means instead of the positive half cycle, we are going to consider only the negative of the half cycle. So this one is visible, the output part.
Reflection coming, ma'am, like what?
Reflection also ticket. Now it is visible, I think. Now it is visible. Okay. Here is the VS, the positive, negative, positive, and negative. So here is our diode direction. So if the diode direction is like this, so we can going to consider all the positive half cycle. When this direction become the reverse, that means we are going to consider the negative cycle. We are going to consider the negative half cycle. So therefore the output will be in series of the positive on the negative pulse depending upon the directions of the diode. The forward directions we are going to consider for the positive half cycle. That means at that time we are going to rectify the output waveform, and we are going to eliminate the negative part. And for the diode become the reverse, so we are going to be considered for the negative voltage, the negative output voltage, and we are going to eliminate the positive half cycle for that. So we can say the voltage across the load. So here in this circuit we can say the output voltage, the V0, which is across the load, and that is nothing but the RL, because here the RL is the load, or we can say the output, and which is consist of the only the one half cycle of the waveform, and which is depending upon the diode itself, because depending upon the diode directions we are going to consider only the one half cycle, either for the positive half cycle and for the negative half cycle for that. So it will occur during the one half cycle of the input voltage. That's why it is named as a half wave rectifier, only because of this concept. Because of the directions of the diode, we are going consider at least one half cycle. That's why it is known as the half wave rectifications. So after we considering the positive half cycle or the negative half cycle, and we need to find out what is the output voltage over here. That means here the no control signal is there. That means you're not going to give the any kind of the pulse. It's not required. For therefore the positive half cycle and for the negative half cycle, there is the pulse. It's not required because there's no signal is there. That's why we are not going to consider. Just to turn on and the turn off while we give the directions of the diode. So we can say that means in this half wave rectifier, we are going to consider the 50% of the time. That means we are considering the positive half cycle is a 50%, and for the directions is reverse. It means we are going to consider the negative half cycle. That is the 50% of the time. While we connected at the output is a resistive load. That means when we connect to the resistive load and we are going to get the high voltage and the current is ripple, okay, is at the maximum. That means we can get the output is voltage, output voltage is the maximum while at the resistive load. While we are going to connect the resistive load. But here the current is going to ripple, ripple at this the maximum. That means at the this one is our maximum point. This one is the maximum point. Here is the pi by 2. So at this point, from 0 to maximum point, the current is going to ripple. It means what is going to be happening is depending upon the current directions itself. That means our objective is all about the AC to DC. That means we are going to equivalent DC value which will drop at these conditions across the resistive load. That means we are only the one half cycle we are considering either positive half cycle or the negative half cycle of the sinusoidal waveform, and that is nothing but the average value. By using the considering the only one half cycle positive with the negative half cycle, and because we have given the sinusoidal input supply over here just to help our to get the average value for the each positive half cycle, and for the negative half cycle we are going to measure the average value of that. That means the maximum value of the waveform. So here is our maximum value for the positive, and here is the maximum value for the negative half cycle, and which is nothing but the sinusoidal functions. And that is what is the value of the maximum value of it? That is the 1. What is the 1? That is nothing but the sine 90 degrees. You can say the pi by 2 is the 90 degrees. The maximum value of the waveform sine function is the 1 value. So here is the 90 degrees. Sine 90 degrees is the value is the 1. That means at the 1 value we are going to give the maximum value of the output. So we need to find out this part is clear to everyone?
Yes, ma'am.
Okay. So we're going to find out the sinusoidal average value. Here is the sinusoidal average value. So our input voltage V is equal to Vm sin omega t. So Vm is the maximum voltage for each half cycle for the positive, negative half cycle. So we are going to find out what is the output. So for the complete cycle, so 0 to 2 pi. And sorry, okay, we are considering the one half cycle. So here is the 0 to pi. So Vm sin omega t, d omega t. So 0 to pi. This is 1 by t. This is the Vs d omega t. So what is the complete t? T is the 2 pi. We are going to conduct for the 0 to 90 degree or 0 to pi It is the Vm sine omega t d omega t. So what will be the value? So from the Vm by 2 pi 0 to pi sine omega t is the d omega t. So can you find out what is the value? So what is the value? So everyone got what is the output voltage? What is the output voltage? Somnath?
Still calculating.
Okay. So everyone please calculate what is the output voltage. 1 by capital T is the complete cycle, this is a 2 pi, and the conduction path we are considering for the half wave rectifier. So for the each positive half cycle or the negative half cycle 0 to pi and Vs d omega t. So what is the supply voltage? Vm sine omega t and d omega t. Just put the value. The V0 equal to Vm by pi. If I am not wrong, the V0 is equal to Vm by pi. So all of you got the output? Hello? ଭାଇନା ଏବେ ତ ମୁଁ ନାହିଁ ମୋର କଲେଜକୁ ଆସିଛି ଆପଣ ସନ୍ଧ୍ୟା ଆସିବେ କେହି କେହି ନାହାନ୍ତି ସେଇଠି ଏଠି ମୁଁ 5ଟା ଗଲା ପରେ ଯାଇକି ମୁଁ ରିସିଭ୍ କରିପାରିବି ତ ଭାଇନା ହବନି Is it done?
Yes, ma'am. Dm by 2 pi volts.
Vm by pi. What about others? So all of you got the output voltage or not? It came Vm by pi. So I'm not finding check.
Ma'am, Vm by 2 pi.
Vm by 2 pi.
Yes, ma'am. 2 pi.
Okay. I don't know, but it came the Vm by pi. Okay, recheck again. So next one is the RMS value of output voltage. So VRMS. So 1 by 2 pi 0 to pi Vm sine omega t d omega t of root over. So can you find out what is the RMS value of the output voltage? So 1 by 2 pi 0 to pi Vm sine omega t d of omega t. Just find out what is the VRMS value. Chinmay Banja,
Yes, ma'am.
did you got the output, RMS value of the output voltage?
Of course, ma'am.
Okay, करो जल्दी.
Root over Vm by pi.
क्या सिला root over Vm by pi.
Yes, ma'am.
Okay, आपने check करो मतलब लागू नहीं correct बच्चों ने आपने check करो. हेलो.
Ma'am, this 0 to pi limit means these are values of
0 to
omega
pi.
t or only omega, ma'am?
Omega t is the value of the omega t.
Then this one correct, ma'am. Means this
Vm
one.
by root over or Vm by pi. Okay. What about Chinmay? So next one is for the RL load. So here is the single phase half wave rectifier with the RL load. That means the output side we are having the load in terms of the R and L. Here is also going to consider for the positive half cycle and for the negative half cycle. So with R load, it is the similar like the previous case. For here, we are going to add the L. So in the positive half cycle, here our voltage source, what is the input voltage source? In that case, the diode is going to on, and for the negative half cycle, is just simply is just the Vs is there. So to decide to design the RL load, we will simplify to check what is the effect of the output voltage when we are adding the L is over here. So before that, we need to consider the two kind of response we are going to find out. One is the forced response. One is the forced response. Another one is the natural response. So what is going to get, because for the while just for only the R value similar with the previous case, for when the L, because we are going to add it. So we get a two kind of the response. One is the forced response, another one is the natural response. So in the force response for this type of the circuit where the current can be exist only after the natural response is to become zero. In that case, then only you can go for the force kind of the response. That means for the previous, the before zero and this will be after zero. After zero, we are going to get the force response. So for the steady state current can be found from this type of the analysis. So here is the circuit where the current is going to flow. That means for any kind of a steady state current, so here is going to be measured the steady state current, which can be the force response actually, because after the zero we are going to go for the force response, and which can be found from this circuit. This is the force current. It's nothing but the Vm by Z, because while added the L, it became the reactance. It is the Z. You can say the impedance. So impedance is nothing but the R plus XL. You can say. So here is the L is the in terms of representing is the XL. So now it becomes the sine of omega t minus of the theta. Why is the omega t minus theta? Because if you remember, we have discussed or we have talked about the forced response, natural response. Before natural response, it is the limited person, because at the point zero and before the zero, whatever the value you are going to got is a natural response. But after getting the response, it's a forced response which must be at the each angle. That means here is my signal for the here is the 0 point is there, and for here it is the pi by 2. Here is the pi. Okay, and this is the 3 pi by 2. Here is the 2 pi. So we can see for the, that's why we are going to add it for the each interval of the angle, what will be the force current over here. And what is the Z over here? It is nothing but the R square plus omega L of square. That is the magnitude. And what is the angle? That is the tan inverse omega L by R. You can say, if you remember, A square plus B square, that the angle becomes theta equal to tan inverse B by L. That is nothing but the tan inverse omega L by R. The force, the current and the force response, we are going to consider the steady state part. And for the natural response, we are going to consider for the transient response. And that can be occurs when the load is energized in that case. So for the natural response, we are going to get in transient response. Going to get the transient response when the load is energized. So here is my load. Here is the load must be energized. Then we can get the natural response, and that is the transfer. That is the concept for the transient. So to get, we consider the natural response. So here diode is there, that means the supply voltage is there. So to get the solutions for this type of the circuit without the source and for the diode. If there is no diode is there and there is the no supply is there, what is going to consider? Here is our IT, the natural response, it is the IR plus DL by dt into IT, which is equal to 0. So natural response go for the transient response, which may be occurred when the load is energized. That means when there is a no supply and a no diode, that means we get the in terms of the R and L, there is nothing but the IR plus DL by dt into I of t. So from this is actually the first order circuit. We can say is the first order circuit. This is the first order circuit. The natural response in terms of the I of, if you are going to solve this first order equations, you are going to get I and the natural response, that transient response is a e to the power minus t by tau, and tau is nothing but the time constant. So here is tau is the time constant, is the omega L by R. This is all about the time constant over here. If you are going to consider the IR dl by dt into I of t. So we can say this is the I of t is nothing but I of t. We can take a common R plus dl by dt. We can say it is the R into I of t plus I double dot, sorry, I dot dl by dt equal to 0. So after solving this quadratic equations, we are going to get I of t equal to a, capital A, it's a constant, we can say e to the power of minus small t by tau. Tau is nothing but the time constant for the transient response. So without the supply voltage in the diode, so we are going to find out what is the natural response, which must be in terms of the transient with respect to the time constant over here. For the RL circuit, become the omega L by R. So after we got the IN, so we are going to find out what is the total T, that is the force current, and this is the natural current. So IF for the force current is Vm by Z sine omega t minus theta plus A e to the power of minus small t by tau. So here capital A is a constant by evaluating using the initial conditions for current. So all of you know what is the initial conditions? How to find out or how to solve these equations? So all of you know what is the initial conditions to find out for the transient response or the steady state response?
Time equal to 0.
Time equal to 0. For the initial condition, time, the t equal to 0. So I of omega t equal to also 0. So can you find out what is the value of the A by using the initial condition? What is the value of A? Capital I of T equal to the forced current plus the natural current. So if you have the forced current, this will be capital Vm by Z sine of omega t minus theta plus for the natural current, you are having the capital A e to the power of e to the power minus t by time constant. So for the initial current t equal to 0, so your work is to find out what is the value of the capital A. What is the constant value we are going to find out. Is it possible to everyone? T value is 0 or I of omega t equal to 0. Is it possible? Can you find out the A value? अरे हबो कि नहीं yes no तो कोई परिबो yes no
Ma'am, A equal to I0 plus Vm by 2 sin phi.
କେମିତି କଲ ତମେ ଏଟା ଭୁଲ ଅଛି କେମିତି ଆସିବ ଏଟା ଆସିବନି ସେତିକି the initial condition I equal to 0 because we took the t equal to 0 and I of omega t equal to 0. So I of 0 equal to Vm by Z sine omega t minus theta plus A e to the power of minus t by tau. So Vm by pi equal to sine of omega t value is equal to 0 minus theta plus a e to the power of 0. So you got Vm by pi sine of minus theta plus a, and I of 0 equal to 0. So what will be the a value? So capital A equal to Vm by z into sine of theta. So here is the capital A value. So Somnath, you can check. So capital A equal to Vm by z into sine of theta. For the initial condition, we are taking the I of 0 equal to 0. ଏବେ ଆସିଲା ତମର?
मैम से vm by z ରୁ vm by pi ଟା କେମିତି ହେଲା?
କୋଉଟା Vm by pi କେମିତି ହେଲା ମାନେ? ସରି Vm by z ସେଟା pi ଲେଖୁଛି. Vm by z. Vm by z sin minus theta plus a. What a value equal to sin Vm by z sin of theta. এটা আসছিলা?
Yes.
So thank you all of you. So all of you leave, okay?